Today we're going to take everything we've learned so far in Chapter 3 about what graphs look like from analyzing the functions and use that information to sketch a graph without a calculator. So the characteristics we need to identify that will help us graph our function are the discontinuities, x and y intercepts, symmetry, domain, relative extrema, increasing and decreasing intervals, points of inflection, concavity, and limits at infinity. The important ones are the ones I have highlighted here. If you don't remember how to find symmetry, you can use, you plug in a negative x for x, and if it equals f of x, then there is y-axis symmetry. If you put in negative y for y, or for the f of x, and simplify it, and if it equals the original f of x, then there's x-axis symmetry. And if you put in both negative x and negative y for the x and y at the same time, and you simplify it, and if that equals the original f of x, then there is symmetry about the origin. We probably don't need to worry about that much. Horizontal asymptotes, vertical asymptotes, those are our discontinuities and our limits at infinity. So just remember those. Let's analyze and then graph this. If we have 2 times the quantity x squared minus 9 over x squared minus 4, the first things we would probably look for are discontinuities. So discontinuities are where the denominator equals 0. So where does x squared minus 4 equal 0? That's going to be at x equals positive and negative 2. And if I factor the top, that's going to be x plus 3 and x minus 3. Factor the bottom is x plus 2, x minus 2. So none of those cancel. So we know that these discontinuities are vertical asymptotes. Then we should probably look for our horizontal asymptotes. We just learned about those limits at infinity. We want to take the limit of this as x approaches infinity, negative and positive infinity. And we can use our shortcut, since this is a polynomial, of just comparing the degree of the top and the degree of the bottom. Since the degree of the top is 2 and the degree of the bottom is 2, then we know that our horizontal asymptote will be at 2. It's just the coefficient of the top divided by the coefficient of the bottom. So we have a horizontal asymptote at 2. That's going to help us set up our structure for our graph. I'm actually going to use a better graph than that. Let's put some axes on here. Okay, so we know at 2 we have a vertical asymptote, and negative 2 we have a vertical asymptote, and at 2 we have a horizontal asymptote. So that's the main structure for our graph. Something else that's going to be helpful is to find the x and y intercepts. So if we put 0 in for x, we get negative 18 over negative 4, which reduces to 9/2. So when x is 0, y is 9/2. So that point, 0, 9/2, which is 4.5, is our y-intercept. To find our x-intercept, you want to set the function equal to 0. So really what we care about is what makes the top equal 0. So that will equal 0 when x is 3 and negative 3. So 3, 0, excuse me, and negative 3, 0 are x-intercepts. So we know our graph's going to hit those 3 points and not cross these lines, these dotted lines. The next thing we would want to look for are critical numbers, so we can talk about increasing and decreasing. So take the first derivative. Low, d high. So when I'm taking the derivative of the top, I'm going to multiply that 2 in, since this is just the first power that's legal. So my derivative of the top, the high, is going to be a little bit easier. Minus high, d low, all over low squared. So simplifying the numerator, four x to the third minus 16x minus, distributing that 2x in, 4x to the third minus 36x and then combining like terms after I distribute that negative, so that'll be a negative 4x to the third and a positive 36x. So the 4x to the thirds cancel out, and 36x minus 16x is 20x over x squared minus 4, that quantity squared. That's my first derivative. So I want to think about where that's undefined. It's going to be undefined at 2 and negative 2 because that's what makes the bottom equal 0. And the top equals 0. So that's where my derivative equals 0 at x equals 0. So my three critical numbers are negative 2, 0, and 2. So I'm going to set up intervals. I have three critical numbers, so I'm going to have four intervals. If I take a number, a test value in between negative infinity and negative 2, like negative 3, and plug it in, the bottom will always be a positive because I'm squaring a quantity. So all I have to really think about is the top. So if the top's negative and I divide it by a positive, I'll get a negative. Picking a number like negative 1, I'll get a negative again. Number like positive 1, I'll get a positive. And a 3, plugging it in there, I'll get a positive. That says negative there. I know it looks like it might be a positive. But so negative 2 here. The first derivative did not change sign. So negative 2 is not a relative max or min. But 0 is a relative max or min because the derivative, the first derivative, did change sign. Since the first derivative changed from negative to positive, that means that the function changes from decreasing to increasing. So the function's decreasing here, increasing here, increasing here. So 0 is a relative min. So this point here is a relative min. We already calculated the y value, so we know this is a min. So it's going to go like that. And then we know the graph increases there and decreases there. So we've got a pretty good idea of the sketch of this graph. But let's also see if we can figure out if we've got the concavity right. So let's do our second derivative. So here's the first derivative. Second derivative. Low d high minus high d low. To do d low, I'm going to have to do a chain rule. So 2 times the x squared minus 4 to the first. So I just took that 2 and put it out in front here. And then times the derivative of the inside. So that's the derivative of this x squared minus 4. All over low squared. So that becomes a 4th power. I don't want to multiply the x squared minus 4 in. So I'm just going to keep that out for a second. I don't want to multiply that 20 in because that's to a 2nd power, so I can't do anything with that now, and I'm not going to distribute this in. Let's see what else happens. This 2, this 20x, and this 2x all multiply together to equal 80x, and then we still have that x squared minus 4. So now these two have a greatest common factor. Just looking at that top there, we can take a 20 out of both terms and an x squared minus 4 to the first. What's left from this, when we take out a 20x squared minus 4 to the first, is just the x squared minus 4 to the first, because we had 2 of them and now we took 1 of them out. And so since to the first, I'm not going to put that in parentheses. Now I'm going to this term. So minus what's left from this if I take out a 20 is 4x. And I've taken that x squared minus 4 out. So that makes it a little bit simpler for me to find my possible points of inflection. If I simplify that, I'll have, I think this was x squared. Let me check. I missed an x squared somewhere, I think. Yeah, x times x, that should be 80x squared here. So 20x times 2 times 2x is 80x squared. So that's still going to have a 4x squared. When I take out a 20 from this, it'll be 4x squared. So x squared minus 4x squared is negative 3x squared minus 4. And that's all over x squared minus 4 to the 4th. So one of those cancels with one of those, so I have only 3 of those. So my second derivative is 20 times the quantity negative 3x squared minus 4 all over x squared minus 4 to the 3rd. So this is undefined when x equals positive or negative 2. So those are possible points of inflection. Also, we want to know where this equals 0. So we want to focus on what makes the top equal 0. So divide both sides by 20. We're left with negative 3x squared minus 4 equals 0. Add 4. We get 3x squared equals 4. Divide by negative 3. We get x squared equals negative 4/3. Well, when you have a squared, it will never equal a negative. If we try to take the square root, we'll get imaginary. So the top will never equal 0. So these are my only possible points of inflection. So if we set up our intervals for concavity using the possible points of inflection and take a test value and plug it into the second derivative, like a negative 3, plug it in here. The top, negative 3 squared, will be a positive 9, so negative 27 minus 4 is a negative on the top, and the bottom, negative 3 in here will be a positive 9, so that'll be a positive. So a negative divided by a positive is a negative. Between negative 2 and 2, let's pick a 0. So we get a negative on the top and a negative on the bottom, so that'll be a positive. And let's pick a 3. Again, we're going to have a negative. So our concavity changes. F is concave up, concave down, and concave. I have that backwards. Sorry, I said that wrong. That is not right. Down, up, down. Sorry. Alrighty, so let's check our graph and see if that corresponds. From negative infinity to negative 2, our graph should be concave down, and it is. From negative 2 to 2, a graph is concave up, and from positive 2 to infinity, it's concave. That shouldn't be very straight. That should be curved down, but that's what happens when I draw on this tablet that I'm drawing on. So, looks like we've got a good representation of a sketch of the graph. So those are the important pieces. We didn't need symmetry, we didn't need domain. It kind of worked out when we found our vertical asymptotes. That helped us with our domain. So those are the important pieces to go through to sketch your graph. For your homework, you're going to have a curve sketching worksheet, which I'll give you tomorrow. Have a great night.